Hello everybody, so this is week 3 of Higher. Today we're going to be looking at intermolecular forces. It's a really important lesson this. The materials that we're going to be learning today are going to be coming up again and again and again. So take your time with this one, it's quite a long one. Go through it slowly. I'll split it up into 2 parts. You may wish to do part 1 today, part 2 another day, it's entirely up to you. So here's what we're going to be covering. 1, we're going to be looking at the types of intermolecular forces. Number 2, we're going to be looking at their relative strengths. And number 3, we're going to be looking at how these intermolecular forces affect the properties of a chemical. And just like as normal, you're going to be needing the following. You're going to need a pen and a paper, and then also your data book. So before we do that though, let's do, as per usual, let's do a little bit of prior knowledge to get our brains in gear. 7 marks this time, some from National 5, some from recent higher lessons. So let's get started. So pause, come back to it in a second. Okay, so we're going from hexanoic acid to butanoic acid. So it doesn't give you the structural formula for these, so you have to kind of remember this yourself and work it out. So here we have on the left-hand side, we've got hexanoic acid, and then on the right, we have butanoic acid, so it's getting smaller. So what's happening to the formula mass? Well, as the molecules get smaller, the formula mass decreases. So we're looking at either B or C. And then what about the solubility? Well, as you get a smaller molecule with the carboxylic acids, they become more soluble. So the smaller it is, the more soluble it is. So therefore, B is the answer. And if you had propanoic acid or ethanoic acid, they would be successively more soluble as it got smaller and smaller. Okay, next one. So quite a lot of information here. It asks you about isobutane and butane. What you need to know is that they are isomers of each other. They have the molecular formula of C4H10. So pause it and then come back when you have an answer. So as these 2 molecules have the same molecular formula, they've got different structures. That's why they're isomers. They are going to have different boiling points, as it's shown by the little table there, and butane has got a higher boiling point than isobutane. Well, why is that? Well, the reason is because it has stronger intermolecular forces. Next question. So again, just pause, and when you're ready, unpause it. So top one, which of the following atoms has got the greatest attraction for bonding electrons? In other words, which is the most electronegative? Where you can go in your data book and you can try and find the answer, or if you are feeling a little bit lazy, you can remember the periodic table, and that electronegativity increases as you go towards the top right. So therefore nitrogen is the correct answer here. Next, what type of structure is found in phosphorus? Well, phosphorus is a molecule. It forms the P4 molecule. It can form different versions of that. We call them allotropes, if you remember from last time. But the most common is the P4, and that is going to have covalent bonds, and it is going to be a molecule. And our evidence for that, if you want to try and figure it out, is to look at the melting and boiling points. Because phosphorus is quite low, it is therefore going to be molecular as opposed to a covalent network. Okay, next one. So I think with this one, it might be useful to maybe draw the ions that we're talking about. That might help you out a little bit with this one. So take a look at this here. This is our phosphorus atom, and it's going to gain 2 electrons. It's got space for 2 electrons in its outer shell. So it gains those 2 electrons, and it forms a phosphide ion. Now the aluminium will lose some electrons. It's going to lose those 3 outer electrons, and it forms the aluminium ion. Now notice what has happened. When we have lost the 3 outer electrons from aluminium, we've removed one of the electron shells. So it's going to be significantly smaller than the phosphide ion. The phosphide ion is actually going to increase in size because the attractiveness, the extra electrons will start to repel each other even more than they were before. So that ion is going to be just slightly bigger than the actual atom. So here is the marking instructions. Have a read of this and see how you got on. Okay, let's move on. I think this is the last one. So circle the structure of the molecule above that contains bonds with the lowest polarity. So how you're answering this is you're looking in your data book, you're going to the electronegativity table again, and you are seeing which of these has got the lowest or the smallest difference in electronegativity. Is it the silicon and chlorine? Is it the phosphorus and chlorine? Or is it the sulfur and chlorine? And it's the sulfur and chlorine. So the sulfur chloride should have been the answer that you got for this one. So hopefully you did well. Hopefully you got 7 out of 7 for this. And let's carry on. So on to today's lesson. So we're going to answer a few questions today. First of all, we're going to figure out why is it that some animals, such as the gecko, can walk upside down. It's not because they got glue on their toes. It's for a different reason. We'll try and figure out what that is today. We are also going to ask the question, why does it rain methane on one of Saturn's moons called Titan? So that image there is an artistic impression of the surface of Titan. And those rivers and lakes and those clouds and those rain droplets, that's all methane, not water. Why does that happen? Why, if you're doing a bit of baking and you get butter on your fingers, why is it impossible to clean off that with just water alone? Why can you not clean off the butter with water? Also, if you eat this fish at a sushi restaurant in Japan and you eat the wrong part of it, why will that kill you? And also, we're going to learn about the science of belly flops. So this is the, I scoured the internet, and this is the best video of belly flop, just in case everyone isn't aware what it is. So let's watch this. Here he goes. There we go. Slow-mo. That would have hurt. Why would it have hurt? Well, we'll figure that out later on in the lesson. And one more time, there we are. So as I said previously, this has been split into 2 parts. We've got first part is types of intermolecular forces, second part is the properties. So specifically for this section, I want you to know the following. Can you tell me the collective term for all intermolecular forces? Can you name the types of intermolecular forces? Can you describe how each of those types arise? Also, can you state and explain their relative strengths? So let's get started. The kind of question you can be expected to be assessed on this, or you can be expected to see to test your understanding of intermolecular forces, is as follows. So we've got a series of chemicals there. Which one of those has got covalent bonding, and also which has got London dispersion forces? So can you identify the intermolecular forces present in particular chemicals? That's what this question is asking. So solids, liquids, and gases. If you start with any gas at a high temperature and you start to cool it down, eventually you'll reach a point where those atoms or those molecules, depending on what you're talking about, are going to be close enough. And when they get close enough, they can start to interact with each other and they will start to stick together. So the liquid part of a state of matter is where all of those atoms or molecules are really close to each other and they're sticking together. And if you cool it even further, you're going to form a solid. But what exactly is it? What are these things that are sticking the molecules or atoms together in a liquid and a solid? What are they? Well, they're the intermolecular forces present between the atoms or molecules. And these things, these intermolecular forces, they are sticking these atoms and molecules together. And we can see them. Well, we can show them in this little animation here. Currently, this is a very low temperature. But if I increase the temperature, suddenly those atoms, let's assume that this is a sample of helium, for example, suddenly the atoms are moving really, really far apart. And they're moving really quickly, but I'm starting to cool it down. And as I cool it down, all of the atoms and molecules start to slow down. And as they slow down, they get closer and closer together until eventually, if you really decrease the temperature, they start to stick together. And at this point, as this temperature has been really, really decreased, we're pretty much at the solid form now. And the reason why it's formed a solid is because we've got these intermolecular forces that are holding all of these atoms together. So here's a set of water molecules. Each of these water molecules has got partial negative, partial positive area. And we have an attraction between the water molecules. This red dashed line, that represents our intermolecular force, the attraction between the molecule. So intermolecular means between, so it's a force between molecules. Now that's different from an intramolecular force. That is a force within a molecule, or an attraction within a molecule. The intramolecular force here is a covalent bond. So just an important distinction before we move on. The bond between the atoms within that molecule is the covalent bond. It is not an intermolecular force. That is between the molecules. Collectively, they are known as van der Waals forces, and there are 3 of them we're going to look at today. The first type is known as London dispersion forces. This is named after Fritz London, a chemist in the 19th century, I believe, and he discovered or theorized these London dispersion forces. So here's how they arise. I've got there an atom of helium. I've got 2 electrons. I haven't shown the nucleus, but so this is just the atom of helium. Now those electrons, you may have traditionally seen a picture of an atom and the electrons are equidistant from each other, one at the top, one at the bottom. And that is the optimal arrangement for those electrons because they're going to repel each other. However, they are constantly moving around the nucleus. They are being bashed and battered and bruised, and as they do so, they move continuously. And it may be that at any one point in time that the electrons are on the same side as each other. When that happens, it means that one side of the atom, and remember we're just talking about helium here, it could be a molecule, but one side of the atom is going to be partially negative. The other side of the atom is therefore going to be partially positive. This is a temporary arrangement. Those electrons are not fixed in place. Because it is a temporary arrangement, this is known as a temporary dipole. And at any 1 second, those electrons can move somewhere else, and that dipole won't exist anymore. But if that if that helium atom comes next to another helium atom, well, we know that like charges repel and opposite charges attract. So those electrons may push another atom's electrons around to its other side. So our initial atom there is on the left, and then that has pushed those electrons on the next atom, the neighbouring atom, around to its side. So in other words, what's happened is we say that it is induced a dipole, and on the second atom there, that is now an induced dipole. So we know that opposites attract. So if we have a partial negative of one atom and a partial positive of another atom, they are going to attract each other. And that dashed line there represents our intermolecular force, in this case, our London dispersion force. But one thing about London dispersion forces is that they're incredibly weak. And if you add just a tiny, tiny little bit of heat, it's enough to break it, which is why helium has a really, really low melting and boiling point. The boiling point, I think, is -269 degrees Celsius. It's as low as you can get. It's the lowest melting, it's the lowest boiling point that we have. So London dispersion forces, every single chemical will experience them because the electrons in any chemical are moving continuously, and as they do so, you will get a temporary dipole. They are individually very, very weak, but collectively they can be very strong. Which is where the gecko comes in. So if you look at a gecko foot, you have these individual little ridges. So each toe there, you have these little ridges. But if you zoom in even further, the ridges are composed of these tiny little, they're called setae, of which are thousands and thousands of them. And then if you zoom in even further, each of those setae has these what's known as spatulas. So if you put all of these together, you are talking about thousands and thousands and thousands of tiny little surfaces. There's a really large surface area there. when that surface area comes into contact with materials such as a plate of glass or whatever it is that the gecko is walking on, we get lots and lots and lots of London dispersion forces, as shown by this little diagram here. So the blue circles there, that represents the atoms on the surface that the gecko is walking on. That's going to be partial positive charge in this example here. The gecko there has got partial negative charges on the spatulas, the end of its toes, and all of these add up together to form a really, really strong cohesive force, or adhesive force rather. And that is therefore why insects, and it's why larger animals such as geckos can walk upside down on surfaces, because they have lots and lots and lots of London dispersion forces. Now, this is a screenshot here from a video of which I've got a link in later on if you want a little bit more information about that. It's really interesting, so I'd advise you to recommend you to watch that later. Our second intermolecular force now. So our next intermolecular force. Here we've got a molecule of hydrogen chloride. We have a dipole over this, and it's a permanent dipole. We've got always the chlorine is going to be partially negative because that can take the electrons towards it as it's more electronegative. And the hydrogen is always going to be partially positive. So we have a permanent dipole. But if we have a sample of hydrogen chloride, we're not just going to have one molecule. We're going to have trillions and trillions of them. And if a partially negative area of one molecule comes into contact with a partially positive area of a different molecule, like so, we're going to get an attraction. Opposites attract. And there's a couple more as well. So this is what's known as a permanent dipole interaction, and it's our second intermolecular force. Now, because the size of our partial charge here is greater than it is in the London dispersion force, therefore this is a stronger intermolecular force. So sometimes just a couple of things to note. First off, it can be referred to as a permanent dipole-dipole, or you may see it written as a PD-PD, certainly by me later on to save a bit of time. And last but not least, they are much stronger than the London dispersion forces. That is because the partial charges are a lot greater than they are in a chemical that's only experiencing London dispersion forces. Now, in this chemical here, we again have a permanent dipole. We've got hydrofluoric acid. The fluorine there is partially negative. The difference, though, in electronegativity between these two, between the hydrogen and fluorine, is really, really large. Hydrogen is 2.2 and fluorine is 4.0. So because the difference in electronegativity is really, really large here, if we get neighboring molecules, we're going to get a really strong attraction. And this might not just be hydrofluoric acid. It could also be between water molecules. So if we have water molecules there, again, the difference in electronegativity between the oxygen and the hydrogen is really large. Therefore, we're going to get a really strong attraction. And a third example would be between ammonia molecules. Now, if we get this setup where a hydrogen is bonded to either a fluorine, or it's bonded to an oxygen, or it's bonded to a nitrogen, we get something called hydrogen bonds being formed, which is a bit of a silly name because it isn't a bond. It's an intermolecular force. It's not a bond like a covalent bond or an ionic bond or a metallic bond. It is an intermolecular force. It is also basically just a permanent dipole interaction, but a lot stronger. And because it's so strong, we therefore give it its own name, hydrogen bonds. So to summarize, if hydrogen is bonded to fluorine, oxygen, or nitrogen, it will form a hydrogen bond, and it is the strongest of the intermolecular forces. And we can see here, so if we have a look at this, we have a sample. So these are water molecules here, and you may see the little dashed line. Those little dashed lines represent the hydrogen bonds. And if we set this off, all of those water molecules, they're bumping around, moving randomly, and as they bump into each other, they attract each other, but then those attractions are broken again as they move away. And if we increase the temperature, we will see that they will move quite a bit more. So we decrease the temperature, as they decrease temperature, they will move slower, therefore the hydrogen bonds will become, will stick together for longer. But if we increase the temperature, here we go, up, 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 those molecules start to move more. As they move more, they will break the hydrogen bonds they had existing. They will go and form new ones with different chemicals, and so on and so on. And if you keep on adding heat, energy, eventually those intermolecular forces will break permanently and you will have a gas. So here's a common mistake that I see pupils making all the time. If you have water molecules here, we've got some hydrogen bonds being formed there. That's the hydrogen bond. That is not a hydrogen bond, that's a covalent bond. So please be aware of that. It is the hydrogen bond that is broken during melting and boiling. It is not the covalent bond. So if you melted that sample of water, if you boiled that sample of water, the molecule, the H2O molecule, would still be exactly the same. It's just it wouldn't be attractive via a hydrogen bond to a neighboring molecule anymore. And a final point about hydrogen bonds is that you can get hydrogen bonds being formed between molecules, different molecules. For example, here the ammonia and the water molecule can form a hydrogen bond, not just between the molecules of the same type. So quiz time. So what I want you to do here is we've got three sets of chemicals. What do we have? We've got methanol, we've got chlorine, and we've got hydrogen sulfide. So three separate containers. Can you name the intermolecular forces present? And I'll give you a little help. The dashed arrow represents an intermolecular force, but there may be other ones there that are not represented, not the dashed arrow, so the dashed line. So pause the video and come back to it in a second or two. So the first one, we have hydrogen bonding. We've got the oxygen and hydrogen within each molecule, really large difference in electronegativity. Therefore, between neighboring molecules, we are going to get hydrogen bonding. We're also going to get London dispersion forces. Everything experiences London dispersion forces. And then it's possible as well, we can see there, we've got a PD, so permanent dipole interaction between the carbon of one molecule and the oxygen of the other. Next, we have chlorine. So this is a non-polar chemical. We're not going to have any partial charges, permanently partial charges. So the only thing that can be there is therefore going to be London dispersion forces. And then last but not least, we have hydrogen sulfide. We've got a permanent dipole, but it isn't going to be a hydrogen bond because that hydrogen is bonded to sulfur as opposed to fluorine, oxygen, and nitrogen. Therefore, we're going to have these two intermolecular forces. Next question, can you place these in order of strongest to weakest? Okay, so in first place, the strongest is going to be ionic bonds, and the intramolecular forces like ionic and covalent bonds, they're going to be significantly stronger than intermolecular forces. Then we have hydrogen bonds, around about 5% strength of an ionic or covalent bond, depending on which source you read. Then after that, permanent dipole, and last but not least is the London dispersion forces. So here's that question we saw right at the beginning. Can you identify the intermolecular forces present in each of those? So pause the video and then we'll go through it in a second or two. Okay, so boron is going to be a covalent network. Neon is monatomic, so that's just going to be London dispersion forces, but there's not going to be any bonds there between the atoms. So it's not that one. Sodium is a metal, so that's not going to be covalent bonding, leaving sulfur, which is a molecule, and because there's no permanent dipoles between the molecules, within the molecules, that's therefore just going to have London dispersion forces. Next question, what is the strongest intermolecular force that occurs between molecules of that chemical, 3-methyl-butanol? So notice how we've got the carbon to oxygen double bond. That section of the chemical there is going to be a permanent dipole. So if a neighboring molecule comes near to it, we're going to get a permanent dipole interaction. And notice there, so this is the right-hand column is the extra guidance that the examiners are giving us, and it says that you allow permanent dipole, and also PD is also acceptable. But I think really it's sensible at this stage just to do permanent dipole, and write that out, even though. Part 2. So that's part 1. That is the type of intermolecular forces. We're now going to look at how those intermolecular forces affect 1, the melting and boiling point, 2, the viscosity, 3, the solubility, and 4, the density of ice. So let's move on. So before we move on, just to make sure everybody's on the same page, when something melts or boils, what happens is the bottom set of diagrams there. So in the top one, we've got methane molecules, and each of the bonds are being broken to form individual atoms. Well, that doesn't happen when something melts or boils. The bottom diagram is more accurate. The dashed blue line, that represents the London dispersion force, in this case, between the methane molecules, and that is what's broken when, in this case, it melts or boils. Okay, so the molecule itself, when it is in the gas state or it's in the liquid state, is still a CH4. The bonds between the atoms are not broken. So just making sure everybody's okay with that. Here are the sort of questions you're going to be asked. You've got 2 chemicals there. Can you explain the difference in boiling points? And can you name the intermolecular forces that are broken when each liquid boils? So identify the intermolecular forces, explain how this affects the melting and boiling point of chemicals. So we talked previously about which is the strongest intermolecular force, and hydrogen bonds are the strongest, and then the London dispersion forces are the weakest. But what exactly does that mean? Well, it means how much heat energy is required to break them. So if you have a chemical which has got hydrogen bonds, it will have a high melting and boiling point, or a higher melting and boiling point, than something which only has permanent dipole or London dispersion forces. So the strength of our intermolecular forces is related to the melting and boiling point. But if we only have London dispersion forces, does that mean that every chemical that only has London dispersion forces has the same melting and boiling point? Well, no, it doesn't. So in the example here, the question is, explain the difference in boiling points between helium and neon. So they've only got London dispersion forces, but they have different melting and boiling points, different boiling points. Well, why is that? Well, it's to do with the size of the intermolecular forces, the size of the London dispersion force. So if we get two atoms of helium, we've only got 2 electrons there. So the partial negative, partial positive charge is always going to be quite small. Whereas in the neon, we've got more, we've got 10 electrons there, so we've got 5 times as many. So the size of our London dispersion force between neon atoms is going to be greater, the strength of it rather is going to be greater. And I've represented that there by a larger partial negative and partial positive. And that explains why neon has got a higher boiling point. There are more electrons present, therefore the London dispersion force is stronger. So a typical question might be this here: what is the relationship between the number of electrons in an atom or molecule and its melting and boiling point? And the more electrons it has, the greater the strength of the London dispersion force. And we've seen this as well in our going down the group in a periodic table. So fluorine, so this is our halogens here, fluorine at the top, bromine right there, lower down towards the bottom. Bromine's a bigger molecule. It's got It's a Br2 molecule. It's got more electrons, and because it has more electrons, you can get a greater partial negative, partial positive charge, and therefore the London dispersion force is going to be stronger. Therefore, more heat energy is required to break it. Therefore, it has a higher melting and boiling point than fluorine does. But what about in chemicals that have the same number of electrons, or near enough the same number of electrons? So let's have a look at this here. Bromine has got 158 electrons. Iodine monochloride has got 162 electrons. So they're around about the same sort of size molecules. But in this case, the polarity is different. Bromine is non-polar, whereas iodine monochloride is polar. So because in this case here, we now have different intermolecular forces, in the bromine, we're going to get London dispersion forces, and in the iodine monochloride, we're going to get permanent dipole, as well as London dispersion forces. The melting point is therefore going to be higher, as shown here. So this now is a good comparison. Because these molecules are approximately the same size, it must be the intermolecular forces that are responsible for the difference in boiling point there. Melting point, sorry. Okay, so here's one for you to have a go at. So we've got two isomers here. We've got ethanol and we've got ether. The boiling point of ethanol is 79 degrees Celsius. Ether, it is minus 23 degrees Celsius. Have a go at this one, please. So here we go. Ethanol contains hydrogen bonds between the molecules that are stronger than present in ether, which therefore requires more heat energy to break. So notice what I've done in this answer. This is usually going to be like a 2-mark answer in a question. So what I've done is I've named the intermolecular forces in both of them. The intermolecular forces in ethanol, hydrogen bonds in ether, LDF, and then I said that therefore the hydrogen bonds are stronger, and therefore more heat energy is required to break them. Okay, so another question here. So state the intermolecular forces present in the following and put them in order of melting point, predicted melting point from high to low. So H2, HCl, and NH3. Pause the video and figure out what the intermolecular forces are and then rank them from high to low melting point. So our ammonia is going to have hydrogen bonds between the molecules, LDF, therefore that's going to have the highest melting point. HCl is going to have PD and LDF, so that's going to be the second highest. And then our H2 is only going to have, it's a non-polar molecule, it's only going to have London dispersion forces, so that's going to be the lowest melting point. Which leads us on to our next thing. Next question, why is it that if you go to Saturn and you are out on one of Saturn's moons called Titan, first of all, you'd have that view, which is quite a nice view, I'm sure. But those clouds there, those clouds contain methane. And that methane rains from the sky to form these hydrocarbon lakes and rivers. And it's been estimated that there's more hydrocarbons on the surface of Titan than there are on the Earth. So why is that? Well, it's to do with the intermolecular forces. If you put water on there, water will form hydrogen bonds, and it takes too much heat energy to break them. So the water, if there is any on Titan, is going to be frozen in the form of ice. However, methane, because it's a non-polar molecule, well, that non-polar molecule will form London dispersion forces. They're really, really weak, as we've said already. Therefore, you don't have to have a huge amount of heat energy to break them. Therefore, on Titan, methane is in the liquid form, which is really cool. And we've seen this. This is a picture. It's a digitally enhanced picture, I believe, to change the colour. I'm not sure this is exact colour, but those dark areas there, those are lakes and rivers of methane. So this was taken by the probe called Cassini, going over the North Pole. And if you want to know more about this, I found it when I was doing a little bit of research for this lesson. I was reading up on this, and I put a link towards the end if you want to know more. It's really, really interesting. Well, let's move on. So that is how intermolecular forces can affect the melting and boiling points of chemicals, but they can also affect the viscosity of chemicals. So viscosity refers to how thick or how runny something is. If something is very viscous, like honey, if something is very thick, like honey, we say that it is very viscous. If it's very runny, like water, we say it's not very viscous. So what we're going to do now is we're going to look at three chemicals. We're going to look at the intermolecular forces present and then figure out how that affects the viscosity. So we've got propan 1-ol. We have got propane 1,2-diol, which is very, very similar. The only difference is here we've got an extra OH group, an extra hydroxyl group on there. And then we've got propane 1,2,3-triol. And now we've got a third hydroxyl group. So let's imagine that we have samples of these chemicals. So here's our sample of propan 1-ol. Now, if you have two neighbouring molecules, the dashed green line there represents the single hydrogen bond that could form. So we've got the oxygen, the partial negative oxygen from the top molecule is being attracted to the partial positive hydrogen of the bottom molecule, a single hydrogen bond. If we have propane 1,2-diol, we're going to have twice as many hydrogen bonds. And if we have propane 1,2,3-triol, we're going to have 3 times as many hydrogen bonds per molecule. So this is going to affect the viscosity, and let's see how it affects the viscosity. So here's a little experiment. Normally we'd be doing this in school, or I could show you a video, but this is perfectly adequate for now. Ball bearings are going to be dropped into a measuring cylinder filled with those 3 chemicals there. I'm going to see how long it takes them to get to the bottom. Off we go. So the propan 1-ol, the ball bearing gets to the bottom really, really quick. Second place was propane 1,2-diol, and propane 1,2,3-triol was in third place. And that's due to the increased number of hydrogen bonds between the chemicals. So here's our 3 chemicals again. The ball bearing in the propane 1,2,3-triol took the longest time to get down, therefore that is the most viscous chemical. And the reason why it's the most viscous is because you have lots of these hydrogen bonds. So the more intermolecular forces present, the more viscous a liquid is. Our penultimate thing that we're going to investigate is the solubility of a chemical. So I've got here some copper sulfate. That copper sulfate has been placed into 2 chemicals. It's been placed into water and it's soluble. On the left hand side we get that blue solution, and then it's also been placed into hexane and it's insoluble in the hexane. Now you probably can remember an experiment similar to this in National 5, and we can now what we're going to do in higher is we're going to investigate what is actually going on. Why is that copper sulfate soluble? Why are ionic solids soluble in water, whereas they are insoluble in things like hexane? So here's what's going on. So I've had to, the diagram I could find was for sodium chloride, but the principle is exactly the same. In any water molecule, you're going to have the negative, partial negative and partial positives, as we know. And we also know that in an ionic solid, we have a positive and a negative ion. Well, if a water molecule comes near to, let's say in this case, a sodium, a positive sodium ion, the partially negative area of the water molecule around the oxygen is able to attract itself to get an electrostatic attraction between the positive sodium and the negative, partially negative area of the water. So each individual ion is then individually stripped away from the lattice structure as the electrostatic attractions between the water and the ions start to form. And we get the positive ions are going to be surrounded by the oxygen atoms. And if we have the chlorine ions, or chloride ions rather, they're negative, so they're going to be surrounded by the partially positive areas of the water molecules, in this case the hydrogen atoms. Not only are ionic solids soluble in water, but also other polar solutes. And in this case, our solute is ethanol. So the top molecules there, they are ethanol molecules. Well, they're polar. They will therefore, in this case, we've got hydrogen bond formed between the oxygen of one molecule, ethanol molecule and the hydrogen of a different ethanol molecule, we've got a hydrogen bond there. We've also got hydrogen bonds between the water molecules. So if they get bashed around and they get bumped into each other, they can break one set of hydrogen bonds and they can form a different hydrogen bond with a different molecule, like so. So now we can see that our water molecules and our ethanol molecules have all been mixed up. It's been stirred up around. The original hydrogen bonds are broken, but because the similar intermolecular forces can be formed, they can both form hydrogen bonds, they can form hydrogen bonds with each other, and this now will completely dissolve, which is quite useful because it allows us to make alcoholic drinks. Ethanol is the alcohol that is present in alcoholic drinks. If ethanol was insoluble, it wouldn't mix at all and we couldn't have alcoholic drinks. Which leads us on to this. Why, if I put butter on my hands when I'm doing some baking or whatever, I can't wash it off with water? Well, it's because a non-polar chemical such as butter will not dissolve in polar water. It just won't happen at all. And you can wash and wash and wash, but you will always have that layer of grease on your hands because the water is unable to dissolve. The reason being is as follows. So the top molecules there, they're not butter molecules, they're hexane, but the principle is the same. The butter is non-polar and the hexane is also non-polar. The dashed blue line, that represents the London dispersion force, and then below it we have the water molecules. Now we could stir this up if this was, we're talking about two solutions or two liquids here, but eventually what would happen is the water would find other water molecules and it would reform its hydrogen bonds. The hexane wouldn't be able to form any bonds or wouldn't be able to form any intermolecular forces with the water. So they would just stay close to each other. And this can be seen in something called a density column. So here we have different layers of chemicals and each layer has a different density. So the most dense is down at the bottom. Each layer is either a polar, then a non-polar, polar, then a non-polar solution or liquid, liquid going all the way up. So this here is a pufferfish, and it's quite cool. If any of you haven't seen it before, Google pufferfish skeleton. It's quite something to behold. And what happens is this pufferfish comes up to any near predators, it blows itself up, it expands, and it makes itself look more scary. But if you eat this fish, it will kill you. So in Japan, if you go to a sushi restaurant, some sushi restaurants will serve you part of this fish, and you have to be a trained chef. You have to get a license to actually serve this fish. Because if you serve the wrong part or too much of the wrong part, it can kill you, and it can kill you because of the chemical that is contained within this part of the fish, and that's known as tetrodotoxin. Now, the tetrodotoxin molecule there is shown on the right-hand side. The structure of it is unfamiliar to you. We've not seen a structure like this before, but what I want you to pay attention to is look how all the way around the outside we have some polar sections. So we've got an NH2, we've got an NH, we've got 4 OH groups, we've got oxygen, we've got hydrogens. These are all very, very polar areas of this chemical. So this is a very polar chemical. And what happens is if you ingest this polar chemical can pretty much go wherever it wants to, because we are largely polar as well. We've got so much water in our bodies that you could consider us to be, this is a generalization definitely, but you consider large parts of our body to be polar. Polar chemicals can dissolve in other polar chemicals. So this chemical here can go into your nervous system and it can cause paralysis, it can cause suffocation, and it can cause, if ingested in too much quantities, in too large quantities, it can cause death. So there we go. So in summary, like dissolves like. However, we need something which is a little bit more accurate, a little bit more higher chemistry level. So what a better explanation would be is, or conclusion would be, non-polar solvents dissolve non-polar solutes. So in other words, the hexane solvent would dissolve oil, for example, and also polar solvents dissolve polar solutes. And thirdly, polar solvents will dissolve ionic solutes. So we're getting towards the end. This was the question we saw halfway through, beginning of this section. Pause the video, have a go. So what you have to do here, you have to try and identify the intermolecular forces present. How does that contribute to the boiling point? Let's have a look at the answers. So the propan-1-ol, that has stronger intermolecular forces, and you have to name them as well. You have to name the fact that in the propan-1-ol you're going to have hydrogen bonds, and then in the ethanethiol we'll go with, there are permanent dipole interactions which are weaker. So if you want to have a bit more time on this, just pause this video and then go over it. Next question. Explain fully why the boiling points of the halogens increase going down group 7, and you have to name the intermolecular forces involved. Okay, so bit of time present in this one. Off you go. Okay, so here we go. What do we have here? So the intermolecular forces increase going down the group. It names the intermolecular forces, in this case it's London dispersion forces, and it says why they are stronger. They are stronger because there are more electrons present in the London dispersion forces. So those are your 3 marks there. Once again, if you want to read this in more depth, just pause the video and then we can move on. So I think this is our last question. Why is ethane 1,2-diol more viscous than propan-1-ol? So pause and then come back when you're ready. So propan-1-ol has fewer hydroxyl groups. So yeah, propan-1-ol is going to have 1 hydroxyl group, whereas ethane 1,2-diol will have 2, and therefore we have fewer hydrogen bonds and within the propan-1-ol and more in the ethane 1,2-diol. Okay, so that is everything. Our very final thing that we're going to go over is why do belly flops hurt? So there's a picture of John there, and why did it hurt, or why does it hurt when you jump into water? Well, you may have guessed this already, you may have been able to predict it. It's to do with surface tension, but what is surface tension? Well, it's to do with the way that the water molecules interact on the surface. They will form hydrogen bonds, but they're going to form hydrogen bonds throughout the liquid. But at the surface, they will form fewer hydrogen bonds because there's nothing above it. Whereas in a molecule within the actual deeper down within the water will form hydrogen bonds all the way around it. So the molecules at the top will form stronger hydrogen bonds. So we get this layer on top of water and on top of other chemicals that form hydrogen bonds, but water is especially apparent. And the layer on top there, they form really strong hydrogen bonds, stronger than they are deeper down, and therefore we have a layer of water. There's our surface, and we see this as well. Little insects can walk or skate along the surface of water. So that's why belly flops hurt, because you have to break through that net of hydrogen bonds, that net of water molecules. Okay, so this is the last thing that you're going to go through. This video is as good as any explanation that I could come up with. So what I want you to do is I want you to just Google this or put it into YouTube. Why does ice float in water? Ted Ed, watch this video. It's also in the Bucksburn YouTube channel playlist. You can find it there. It's a really good explanation as to why ice floats on water. It's as good or as better as I could do. So I think this is worthwhile watching. So if you guys want to know a little bit more about what we've... And then lastly, totally unrelated really to our course, but still really interesting. This is the stuff that I was getting a bit of research for the lesson. Lakes of Titan, so that's the lakes out on Titan, the moon, Saturn's moon with its methane lake. Superfluidity, if you don't know what this is, I really recommend you have a read on that. And absolute zero, so I imagine most physicists will be familiar with that. But still, the history of absolute zero is quite interesting. So have a check out on those if you're interested. And that is us at the end. So thank you very much if you've got this far. There will be a Google form associated with this, so get that into me as soon as possible. Get your questions to me and I will get back to you as soon as possible with the answers. So thank you very much.